ho, you guys made it. This is content for exam 3 and it should be the end of content all the way to lead you into your final. So, yeah. Yeah, this should be the last Biochem 1 video you guys should ever see, and then I have a whole list of Biochem 2 videos for you guys to watch next try if you ever get stumped or anything, because I will be done tutoring. I apologize for making this video really late. It's been a busy week, and then my nap went a little longer than expected. So here I am. All right. Well, I'm not going to waste any more time. Turn it on 2 times speed. You guys just get flying through this because I know we're on crunch time now. So, oh, whew. All right. We're going to be talking about bond dissociation energy. So, bond dissociation energy is basically just the energy that is contained within bonds between structures. And you guys can see a little example right down here. There will be a little bit of math on your guys' exams, so just be prepared for that. So I'm going to try and go as thorough as I can be with also saving time. So let's talk about it. So we're going to be talking about making and breaking bonds. So anytime we think of breaking a bond, we should be thinking of an endothermic reaction. And the reason we're thinking of an endothermic reaction is because we have to input energy into that bond and overpower that bond energy to get that bond to break between molecules. If we, let's say a bond has 40 kilojoules of energy and we only put 20 kilojoules of energy in there, it's not enough energy to really break that bond because we're not overpowering that bond strength of 40 kilojoules. Now, if we put 50 kilojoules of energy into that bond, boom, bada bing, bada boom, we release it, we break apart the bonds, and we release these particles. So if we look, biggest thing we want to know is the energy of our products will be more than the energy of our reactants when we put energy into there, and that is just because we're breaking bonds, because anytime anything is bonded together, it is going to be a lower energy form compared to if we break those molecules apart and they're two independent particles. This same concept has been seen before when we were talking about amphipathic agents and micelles. When we had free-floating amphipathic agents, those agents were a higher energy form compared to when they bound together to form a micelle and became a more stable and low energy form. So if you guys wanted to think of a graph for endothermic reactions, we are going to be thinking of this graph right here, because our products, and if we just do energy right there, our reactants are going to be a lower energy value compared to our products because we have to input energy into these reactants to break the bonds. And when we release the products or the two molecules bound together, when those are two free-floating particles, we are going to have higher energy products compared to our reactants. Now, on the completely opposite side of the spectrum, we're going to talk about making bonds, and these are going to be exothermic reactions. The energy of our products is going to be less than the energy of our reactants, and this is because the system loses energy to the surroundings. And this is because we are taking two individual molecules. So if let's just go exo, da, 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 da. Let's say we just go a carbon and a carbon. We just make two carbons bound together. Probably doesn't happen in nature, but just for the sake of this example, we have two independent free-floating molecules here. And these two free-floating independent molecules are high energy because there's more, I believe the proper term is entropy in the system. These guys are flying around, they're bumping into things, creating energy. They're just highly energized forms. And I mean, I guess the most basic example you could look at is honestly the conversion of water into a solid, where you're taking water where these particles are a little bit more spaced out, provides more fluidity for the compounds of water. But as soon as hey, you lower the energy down, you freeze it, you put this block of, or this container of water in the freezer, you are cooling down all those particles. You're reducing the energy that those particles have to move around freely. And as a result, they're going to turn into ice. So this concept of lowering our energy forms kind of holds true to exothermic reactions. And if you want to look at a chart for that, it's going to be this little chart right here that I'm drawing on. And so for an exothermic reaction, which is always going to have a negative energy value, endothermic is always going to have a positive energy value. When we think exothermic reactions, we should always think of high energy products combining and making bonds to become a more stable and lower energy form, such as down here. If there's any questions about that, please reach out to me. All right, let's look at some examples here of the math you guys are going to be doing. So most of the time, you guys are going to see an example like this. He's going to give you where's my laser pointer at? He's going to give you a reactant side and he's going to give you a product side. And if we look over here at our reactants, we can see a CH4 and a Cl2. And then if we look at our product side, we can see a CH3. Oh, wait, Cl. Where'd that fourth hydrogen go? Oh, wait, it's over here bound to the chlorine. So what we can tell from these products right here is that bonds were broken in here over on our reactant side to create new compounds over here. So on the left-hand side, we know we are breaking apart some of those molecules and breaking some bonds to release some of these particles out into free space. So that means we have to input energy into the system. We have to put a positive amount of energy into the system to break those bonds. So therefore, the reactant side over here is going to be considered endothermic. But if we look over here on our product side, we can see that we are making new molecules. We are bounding that free-floating, I believe it's chlorine, free-flowing chlorine over onto that CH3. And we are taking that hydrogen that we released over here from CH4 and binding it on to this chlorine free-floating molecule over here. So since we're creating new bonds and creating new molecules, whatever you want to call it, we know that that is an exothermic reaction because we're taking these once free-floating particles that we released over here and lowering down their energy and making them into a more stable form by attaching them onto this other molecule. So that will be considered an exothermic reaction because technically with some of our free-floating particles over here, our reactants, our products are a much more stable and lower energy form compared to our reactants. So how would we approach that in a problem? So he will give you listings for bond energies within it. So for the sake of this example, we'll just look at the pre-given values here. We can see that CH4 has a bond dissociation energy of positive 437 kilojoules. That means if we break those bonds or when they go under an exothermic reaction, the total amount of energy that we have to input is around 437 kilojoules. So boom, lock that value into your brain. Same idea goes here for 244 kilojoules. And this positive energy is the energy that we are putting into the system. We are taking energy from the surroundings, putting it into the system to break up these bonds. Now, if we go over and look on the product side, we can see that when these new products are formed, these negative values are the energy being released from the system into the surroundings. So we know here, positive values, energy inserted into the bonds to break them apart. So now when these new bonds are made, they are going to release energy back out into the system. So we know when CH3Cl, when those bonds form together, we are going to release 353 kilojoules of energy, but it is going to be a negative value because it is an exothermic reaction. Exothermic reactions are negative, and that means we are releasing this energy from the bond back out into the system or back out into the surroundings. Same concept goes here for HCl. We know when HCl or hydrogen and chlorine bind together, when that bond is formed, we are going to release 433 kilojoules of energy, which will be a negative value because we are releasing it from the system back into the surroundings. And what he'll ask is the total energy of the system. And it's pretty simple. The total energy of the system is going to be taking the positive value of the endothermic reactions over here on the left-hand side and just subtracting or adding it with the negative value over here on this side. So we know when we add these two together, we are going to get a total of 105 kilojoules, which is still signifying that we are more on the exothermic side of things. So basically that is, with that value, which is delta H, that is basically just representing the total difference between the reactants and products. And if we have a negative value like here, negative 105 kilojoules, that means we're kind of looking more at an exothermic reaction because if we look over here, our reactants, again, higher energy form over here, and our products are now a lower energy form, our net total kilojoules is going to be negative because our products have a lower energy value compared to our reactants. So anytime you see a negative kilojoule value for delta H, your first thought should be thinking of, oh, this is an exothermic graph. I see a negative, I know it's going to be exothermic, and I should be thinking that my products are a lower energy form compared to my reactants. Now, let's say this was a positive, that's saying that it's like, hey, that's more of a endothermic reaction. We're maybe putting in almost too much energy into this system, break these bonds apart. And our products are going to have a higher, that means our products had a higher kilojoule value compared to our reactants. And if you look over here, our reactants, hey, our reactants are a lower energy value compared to our products, which is signifying an endothermic reaction. And that this positive value right here can basically be the same as just taking these products over here and just reversing the system right there. We have to put the same amount of energy into these molecules right here to break them apart and convert them back into these other forces over here compared to the other way around. And so our delta H is always going to be equal to total energy of bonds broken compared to total energy of bonds formed. And while we're here, I do want to touch on this graph because it is a big concept. So this graph, again, is kind of like the graphs I was describing up here. It's basically just the total energy of a system between reactants and products. And what we can tell over here is we can already see that, hey, our products down here are a lower energy form compared to our reactants. And that should be, our first thought should be an exothermic reaction. So going off of this, our delta H will always represent the difference between our reactants and our products. This value will never change no matter what, because all these systems have a set number of energy that we can either insert and release, and rules of nature really do not change that much. The only thing that we can modify from here is our activation energy. And this is the initial burst of energy that we need to initiate a reaction, whether it's making bonds, whether it's breaking bonds. Our activation energy is the only modifiable factor on this chart right here. If you see delta H, you know that is a law of nature and that does not change. That will always be between reactants and products, but our activation energy is always modifiable, and that is due to enzymes and different catalysts that can speed up reactions, slow down reactions, and we're going to get into that into a second. But when you think delta H, just know that never changes. So now let's talk about activation energy. Activation energy is the energy it takes to initiate a reaction. The higher the activation energy, the harder it is to have a reaction, which makes sense because, like, let's say this is our set reaction right here. If we need, let's say our activation energy comes all the way up here and comes back down. What you guys already noticed is, hey, our delta H does not change, only our activation energy changed. And basically what this is saying, when the higher the activation energy, the harder it is to have a reaction. If we have a higher activation energy, that means we need such a higher input of energy to initiate this reaction. So this black little lump right there, that is representative of a higher activation energy. And compared to this little hump right here, this little hump does not need nearly as much activation energy to get this reaction to go. So the smaller the activation energy, the quicker these reactions will fire because we need to input less energy. The higher the activation energy, the slower or longer these reactions will take because we have to input so much more energy into these systems to get these reactions to go. We'll talk about Boltzmann distribution. Boltzmann distribution, I can guarantee you're going to see this on your quiz, and it's a great concept to understand. But the higher the activation energy, the fewer particles that have the required energy. So basically what this is saying is if we have two boxes of the same number of particles, box A has a low activation energy, box B has a high activation energy. It's basically saying over in box B, these particles do not have as much energy compared to box A. And as a result, it's going to take a lot more of these particles to bounce together and a little bit longer to get the required energy to initiate some reactions to occur in box B compared to box A, to where if we have box A particles have each individual particle has the required energy or a higher energy per particle compared to box B, so we need less reactions to occur or less connections to occur over in box A to get this required energy to get this reaction to go. And then if we increase the activation energy, we decrease the rate of reaction. We've already talked about this. Basically with this little example right here, smaller the activation energy, the quicker the reaction will go compared to up there. All right. Let's continue to talk about Boltzmann distributions. So the Boltzmann distribution, basically the rate of a reaction is determined by A, the number of collisions, the energy factor of the collisions, and the orientation factor. So the number of collisions is basically saying how often do these particles bounce into each other? If they are bouncing into each other a lot, that means a lot more energy is occurring because a lot more of these particles are hitting each other at a lot higher of a frequency. Secondly, the energy factor of collisions. If each of these individual particles have a high amount of energy, it only takes a couple of collisions to get these reactions to go. But if these particles have a low amount of energy, they're going to have to collide a lot more to create the desired energy to get the activation energy to initiate. And lastly, the orientation factor or the complexity of a system. It's basically saying, like, if I had a jar full of marbles and I shook them around, like, I mean, this jar was filled to the brim with marbles. And if I start shaking them around, these marbles are going to be connecting and clashing all over the place. And there's going to be such a high number of collisions between these marbles. But let's say I just go to a warehouse with a handful of marbles and I just chuck them in the air. There is so much space that these marbles will barely connect with each other. So the rate of collisions will be decreased, and the total number of energy that we could be producing is significantly decreased because we are decreasing the number of collisions based on the orientation factor of these marbles. Secondly, if we increase the energy factor, we increase the rate of collisions, and this is basically saying that if we add energy to the system, we are adding energy to these marbles, and these marbles are going to be connecting with each other a lot more and transferring a lot more energy. If we decrease the activation energy, we increase the rate of the reaction. And basically what this is saying, and we'll just use this chart over here now, if we decrease the activation energy, so let's say this is our normal activation energy right here. This is our normal activation energy, but if we decrease the activation energy and we move it down to here, the difference between the desired energy needed to initiate this reaction significantly drops. So we need less of an input of energy to get this reaction to go compared to our normal one, which is up here. And if we increase the number of particles, we increase the rate of reaction, because the more particles we have, the more collisions that happen, the more energy transfer that happens, and the quicker we will be able to get to our desired activation energy. So now let's look at the Boltzmann distribution, and it's taking on a couple of factors. What I really want you guys to pay attention to is the x-axis and the y-axis on over here. So over on this side, we can see on our, oh man, I messed that up. I'm shaming my trigonometry teacher right now. All right, on the y-axis, we have number of particles. So again, based on the rule, the higher number of particles that we have, the quicker the rate of the reaction is going to occur. And then if we look on the x-axis, it's the total number of energy needed for the activation energy. So this x-axis right here is going to be the exact same as this y-axis over here on a regular just distribution graph. So what we can see is these red little boxes right here are direct representations of our activation energy over here on this graph. So let's take a peek at it. First thing I want us to look at is E1. And what we want to notice about E1 is, A, compared to E2, we have a higher concentration of particles, and based on the rule of the Boltzmann distribution, the increased number of particles that we have, the rate of the reaction is going to increase. So we can already see right here that our energy levels is a little bit less than E2. And over here, we can see over here for our activation energy, our E1 level is a little bit less than E2. And this is using that concept into play, because if with the high number of particles we have right here, we do not need as much energy to get this reaction to go. Compared to if we look at E2, we can already see right here, we have a higher activation energy, which already means we need more energy inputted to get this reaction to go. But we can also see over here on this graph that E2 does not have as many particles compared to E1, and as a result, our activation energy is going to be a little bit higher because we do not have as much energy compared to E1 to get this reaction to go. So the less number of particles we have, the more activation energy we need to get this reaction to go. The higher amount of particles we have, the less energy we need to get this reaction to go, and E1 will be a lot quicker of a reaction compared to E2. Oh man, That's a lot of words. Biggest thing I want you guys to notice over here on this graph and this exam and this topics, X and Y axes are a big concept. So I'm going to be going through it and I might sound repetitive, but I just can't emphasize enough how important it is to understand the X and Y axes and what's on them. All right, carrying on. Catalyst. Actually, I'll let you guys read through this on your own time. It's basically me repeating a ton of stuff I already talked about up here compared to the activation energy. So just read through that. So now we'll move on to catalyst. And catalyst, basically enzymes. And what enzymes are able to do is they are able to decrease the activation energy of our reactions and allow our reactions to occur a lot quicker and a lot more efficiently compared to if we did not have an enzyme. And enzymes are everywhere in our body, and they're referred to as catalysts. So, used to modify the rate of the chemical reaction, they are involved in the reaction, but do not undergo the reaction. These enzymes are basically just a helping hand, but they are not modified at all. They can be used over and over and over and over again, and they're unchanged during the reaction. Biggest thing, again, I can't emphasize it enough. It does not affect the energy change or delta H. It only affects the activation energy. So to beat a dead horse here, our enzymes are only going to be impacting these little humps right here. It is going to be modifying our activation energy, but it is not going to be modifying our overall energy change because we cannot change the laws of nature. We cannot change the required amount or the predetermined amount of energy that is released and absorbed between these molecules. We cannot change the overall energy change. We can only impact the activation energy and speed up or slow down the reaction. Cool. All right. Enzymes, biological catalysts. They are always peptides, regulated and controlled. They regulate and control metabolic reactions, and they will always end in ACE. In Biochem 2, this will be a huge concept, but also we see peptides. What are peptides? Peptides are amino acids that can be transformed into proteins. So what does that mean? Enzymes are considered proteins. And when you get a super high fever, the reason it is dangerous is because the high increase in temp denatures our proteins. Well, if our proteins are being denatured, what happens to our enzymes? Oh, wait, they become denatured too. Oh no. So that's why a lot of fevers are dangerous because our enzymes are no longer active in some functions of our body. And as a result, a lot of these reactions we have going on in our body that are used to having an enzyme and having a decreased activation energy, as soon as those enzymes are taken away, our body needs so much more energy to get some of these reactions to go, and that can shut down some of our systems in our body because sometimes we don't have enough energy to spare to match these new energy thresholds. So that's why enzymes are so important. They make the reactions inside our body so much more efficient. Oh man, that was a soapbox. Okay, here's a complicated subject that I noticed last try specifically that some people had a very hard time understanding. So I'm going to try and make this crystal clear. I'm going to repeat myself out the wazoo, and it is just going to be a lot of fun because I really do like this stuff. I really like enzymes. So, um, let's just talk about this little thing right here because this will for sure be a question on your guys' exam. So this is an enzyme substrate complex. So basically a substrate, what it will do is a substrate, actually I'll just, whoop, it's going to come in, find an enzyme, it is going to react with that enzyme, and we are going to create a product. So basically enzymes allow for substrates to change form and become final products. And that is basically just called an enzyme substrate complex. So basically when an enzyme or when a substrate comes flying by, it finds an enzyme and goes, hey, I want to bind to you. I want to become a better version of myself. And the enzyme's like, all right, come on, come with me. And the substrate binds to this enzyme and the enzyme's like, all right, we're going to give you a new hairdo and you're going to be better than ever. And the substrate's like, sick. So after the new haircut, the substrate is a new product because it's a new version of himself. He did some self-help books and there you go. He's a better version. So this enzyme substrate complex, we can see Ka, Kb, Kc, and Kd. And basically this is just talking about an enzyme, a substrate binding to an enzyme and what happens. So Ka is going to represent the forward motion of when our substrate binds to our enzyme. And we can see that now our substrate is bound to our enzyme and it's going to get that haircut. And then if we want to progress to where the enzyme releases the product or the new version of that substrate, we will use the value of Kc because the enzyme and substrate, the substrate changes form within the enzyme is like, all right, you're better, let me let you go, and the enzyme releases the product. So Ka to get the enzyme bound to the substrate, and then Kc to get the enzyme and substrate to release and allow the enzyme to release the product. But we can also see Kb. So Kb is basically representing the backwards motion of the enzyme substrate complex. So let's say we did Ka and we got here and the substrate's like, hey, let me get a hairdo. And the enzyme's like, all right, $20. And the substrate's like, hey, I don't have $20. Can you do it for free? And the enzyme's like, nope, get out of here. The enzyme will kick the substrate back out and it will release the substrate back out into open space and the enzyme will once again be free. And that will be represented by Kb or the backwards motion. But we have one last remaining aspect right here. We have Kd, and Kd is going to represent the backwards motion of the enzyme and the product. But the only thing is that never happens because enzymes have specific binding sites. So that original substrate can bind to that enzyme, but once it changes form and gets that new hairdo, it's kind of like this enzyme right here just forgets who that person is, and this product will be like, hey, can I get my old haircut back? Can I become the person I was before? And the enzyme's like, who are you? You're not allowed here. Get out of here. Go, go, go. So this product will never ever be able to bind back onto this enzyme. And as a result, Kd will always be zero because this backwards motion of an enzyme and product and the enzyme converting the product back into a substrate never occurs. If I had to drill one thing into your brain, Kd will always be zero because this little thing right here it never happens. Never happens. All right. Yeah. All right. Moving on. So now we're going to be talking about reaction velocities. And reaction velocities are basically how quickly a reaction occurs when the substrate binds to that enzyme. And there's three different phases we have to know. We have to know what happens before. Actually, I should probably describe what Km is. Km is the affinity that an enzyme has for a substrate. So what I want you guys to know is the lower the Km equals higher affinity. So if an enzyme has a very low Km, that means it's just itching to get a substrate. That means when a substrate comes by, that enzyme is immediately latching onto it. And we need a very low level of substrate for those enzymes to be like, hey, substrate, come here, let me give you a new haircut. But if we have a high Km, actually, let me make sure I'm fact checking myself here. Smaller Km, the greater affinity for an enzyme substrate complex. Yep, I just don't want to lead you guys in the wrong direction. So if we have a super high Km, that means the affinity that the enzyme has for an enzyme substrate complex is very low. And that means the enzyme really does not want to bind on to that substrate at all. And realistically, I want to talk about Biochem 2 terms here to really tie it all in, but I just don't think it'd be beneficial for us right now. Basically, if an enzyme has a super high Km, which means it has a low affinity, that means we need so many substrates. That means we need to pack the house with substrates to finally get the enzyme to be like, all right, I'll do some work. But like if the enzyme has a very low Km and it has a very high affinity for the enzyme substrate complex, you only need like one or two people inside that venue for the enzyme to be like, all right, let's get this crap going. Let's get going. And honestly, I'm making up all these examples on the fly, so I really hope they're making sense. All right. I got off on a huge tangent there. Okay, Km. Km we know represents the affinity that an enzyme has for a substrate. So we're going to be looking at three different phases of this reaction here. We're going to be looking inside this box, which basically what this box represents is any substrate value less than the desired substrate value of Km. So anything from this line and back is less than Km. Or it means our substrate level is less than Km or the desired value. When we are directly at Km, that means the substrate level is equal to Km. And then anything past Km is going to mean our substrate value is larger than Km. And each one of these is going to have a different value in terms of reaction velocity, or how quick a reaction is going to occur. So first, let's talk about less than Km, or our substrate level is less than Km, which will be represented by right here, or represented by this little green box. So we can see that our substrate level is less than Km. And what that is going to do for our reaction velocity, or this little graph aspect right here, our velocity of our reaction is going to be equal to Ks, or the concentration of our substrate. Our reaction in this area before Km is only determined by the amount of substrate we have. So if we only have, like, let's say 3 substrates, our reaction velocity is only going to be like 0.3 of maximum velocity, because we have such a little amount of substrate. But as we keep on adding substrate, our reaction velocity is going to keep on getting a little bit quicker until, oh, look at that. We finally reached a point to where our substrate level is equal to Km. So let's move on to the next stage. Our substrate level is equal to Km. And what that is going to be equal to is half of our maximum velocity. Anytime our Km hits this blue graph right here, like even if our Km was over here and it hit the graph up here, our Km value when it hits this point or this point will always be equal to half of the maximum velocity of a reaction, or Vmax, not Wmax, Vmax divided by 2. Anytime our substrate level is equal to Km, our maximum velocity will always be Vmax divided by 2. So do a quick refresher. Anything less, I wish I could change the size of this highlighter. Okay. Anything less than Km, our reaction velocity is going to be determined by the concentration that we have of a substrate. The more substrate we put in, the quicker our reaction velocity is going to get. Then, once our substrate level is equal to Km, we know we have reached half of our maximum velocity, no matter what, Vmax divided by 2. Anytime our substrate level is equal to Km, our velocity is always going to be Vmax divided by 2. Now, lastly, what happens if we add even more substrate and we get past our Km? We have more substrate levels than our Km, and our enzyme know what to do with. Well, we're at maximum velocity. So anytime our substrate level is greater than Km, I want us to know we have reached our maximum velocity of a reaction. And that just means our reaction is off to the races. Our enzyme is just pumping out products like nothing else, and we're just as efficient really as we can be. So as a quick refresher, anything before Km, or when our substrate level is less than Km, our reaction velocity is determined by the concentration of a substrate that we have. If we only put 2 in, our reaction velocity is going to be down here. If we put 4 in, our reaction velocity is going to increase to up here. And then let's say our Km is 8. Well, once we add 8 millimoles of a substrate, we know that we have reached Km, and our max, or our velocity of the reaction, is going to be half of Vmax. And then as soon as we add anything greater than 8 millimoles, we know that our reaction velocity is going to be at maximum velocity, and we are at the quickest rate that this reaction can go. All right, a lot of talking. We're getting there though. And basically this is just a comparison of, this is just a good recovery on maximum velocity charts. So we can see right here that our Km is significantly less than our Km2 over here, which means we don't need as much substrate to get to our Km. So we can add less of an amount of a substrate here, and we can reach maximum velocity that much quicker. And then once we pass Km, we know our maximum velocity can occur a lot quicker compared to this other reaction right here, to where we have to add such a high amount of substrate just to get to half of our maximum velocity, or equal to Km. And then we need even more substrate to even get to our maximum potential. So that's just a good comparison. All right, coenzymes. Coenzymes are not an enzyme, but they are part of an enzyme system. They are not a polypeptide, and they are an organic molecule instead, very similar to iron. And you could refer to them as oxidizing or reducing agents. And if it is not an organic molecule and instead a metal ion, they are referred to as cofactors. So coenzymes equal organic, like down at Whole Foods, or if we want to refer to it as a cofactor, is referred to and telltaled by a metal ion. Good differentiation to make right there. Besides that, that's just going to be some terminology we need to use. And honestly, no, we might talk about it in a little bit. All right, cracking more. Lineweaver-Burke plots. Basically, we are taking this graph and we are linearizing it, and just Lineweaver-Burke plot. We are just linearizing our reaction velocity charts. And as I said before, pay attention to X and Y axes. This is what I'm talking about. This is where it is going to become so important, because he will most likely ask you questions about the axes of these charts. I apologize if you hear me sipping a lot. I'm having a little glass of Four Roses. Not going to say specifically what that is, but if you guys know, you know. All right, let's move into inhibition. So this is where Lineweaver-Burke plots are really going to come into play. So we're going to talk about different types of inhibitions, and basically inhibition is talking about shutting down an enzyme. Basically taking an enzyme and saying, hey, slow down, shut off, we don't need you. And these inhibitions are super important for a lot of the processes inside our body. And when we get to allosteric inhibition, I will be going crazy on soapboxes, because it's just so cool, especially when you get into biochem 2 and start understanding how a lot of this stuff works. So competitive inhibition. The inhibitor structurally resembles the substrate. So basically what this is saying is our inhibitor, or whatever is going to shut down this enzyme, looks very similar to our substrate. And you can kind of see in this little example right here that our substrate looks like a little pizza pie, and our inhibitor also looks like a little pizza pie. So if our inhibitor comes in and binds to this enzyme, it is just clogging up the active site for our substrate to come in. So if our inhibitor was here and our substrate tried to come down and bind to it, it wouldn't be able to, because this active site is clogged up. So a couple key things we need to know. Our inhibitor structurally resembles the substrate. We can reverse this kind of inhibition by increasing our substrate concentration. So if we have some inhibitors floating around, they're starting to clog up our enzymes, we can increase our substrate concentration to eventually override our inhibitors, and our enzymes will spit out these inhibitors and say, crap, we have a backup of substrates over here that we need to convert into their new hairdos and give them a new personality. So, hey, let me get rid of this inhibitor and let me take this substrate and start doing conversion, because we're on huge back order right now. That's basically what's going on. And then we have a constant Vmax. All these little highlighted areas that I have are big differentiators between these different types of inhibition. So please, and also this one right here, I'm gonna do this one just because it's a good one. Please pay attention to these little stars that I'm putting down right here, because these are fantastic differentiators. So when it's talking about a constant Vmax, basically what they're saying is our velocity right here really does not increase or decrease. So basically we can see right here is that our velocity, or 1 over Vmax, also bing, 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 1 over Vmax, 1 over substrate, memorize these axes. Our Vmax really does not change too much, because instead of reducing the speed at which these enzymes occur, we are just clogging. All we're doing is clogging the site, but we are not really monkeying with these enzymes here. We're not shutting down their function. We're basically just clogging them up just so a substrate can't bind. So that really won't monkey with our velocity at all, because if our velocity was to be messed with, that means we would have to modify this enzyme or change something within this enzyme to get it to slow down or have its velocity occur or change. But Since no conformation or malformation of this enzyme is happening, our velocity really is not monkeyed with at all. It's just the rate at which enzymes, or it's the rate at which substrates can bind to it. So maybe the speed or the substrate binding speed will slow down, but the enzyme reaction velocity really will not slow. And that is why our Vmax remains constant, because our velocity really does not change. But what I want you guys to know is we are seeing a left-hand shift right here. So with this left-hand shift right here, basically that's really all I want you guys to know. If we see an increase in our inhibitor level or an increase in the concentration of these guys right here, all I really want you guys to know is our graph is just going to rotate up and to the left, which means our substrate concentration that we need to override this mechanism is at such a higher threshold compared to if we didn't have it. Like down here, our substrate levels can bind and we can get reactions all the way out to here no matter what. But as soon as we have a higher presence of an inhibitor, we need a little bit higher of a concentration to go, and our reaction, just like the rate at which these reactions occur, slow down a little bit because these inhibitors are binding onto these sites. So competitive inhibition, biggest thing you guys need to know, the inhibitor structurally resembles the substrate. The inhibition can be reversed by increasing the substrate concentration. Our Vmax remains constant. Huge thing right there, constant Vmax. And then our inhibitor binds to the active site, which is just the active binding site right there. Cool. Just a little refresher. Smaller the km, the greater affinity of an enzyme for a substrate. Talked about that quite a bit. Moving on, non-competitive inhibition. So, non-competitive inhibition is basically saying we are going to shut down this enzyme, but we don't need to clog up the site. We can shut it down from somewhere else on the enzyme, and there's a secondary site. So, biggest thing I want you guys to know for non-competitive inhibition, our inhibitor is going to be a heavy metal or a Lewis base. Secondly, I want you guys to know it binds to the allosteric site, which is not the active site. And furthermore, what happens? We change the tertiary structure. We change the structure of this enzyme. We modify this enzyme. So compared to up here to where we just clogged the active site, which is right here, but really didn't monkey with the enzyme, and that's why we have this constant Vmax. This rule changes down here because now we are changing the structure of this enzyme. We are changing the molecular function of this enzyme. And as a result, our Vmax is going to decrease. And we can see that right here. Our Vmax is slowly going to become less and less and less and less with the more non-competitive inhibitions we have. So, how I said just a second ago, our inhibitor is going to be a heavy metal and it's going to bind to the allosteric site. An allosteric site is going to be a site that's not the active site. So it's basically just going to be a secondary site for these heavy metal ions to bind onto. So we can see right here, if I were just to highlight this, our active site is going to be where the substrate binds to. And similar up here to competitive inhibition, our inhibitor bound to the active site, or where the site that the enzyme, or I'm getting all mixed up, where the substrate binds onto our enzyme. That is referred to as the active site. But for non-competitive inhibition, this means our inhibitor is not competing with our substrate, and as a result, we are binding to an allosteric site or an alternative site on this enzyme to shut it down. So it will bind on the back end of this enzyme, and basically what will happen is this inhibitor will come in, bind to this allosteric site, and we will change the tertiary structure or the function of this enzyme. And what that is going to do is it is going to prevent, basically, I'm just going to do this. It is going to prevent this pathway from happening. It is still going to allow our substrate to bind onto this enzyme, but since we changed the tertiary structure and made this enzyme not functional, this enzyme cannot convert this substrate into its product. It still allows the substrate to bind, but does not allow the substrate to change character because the enzyme's tertiary structure is monkeyed with. And that is why our Vmax decreases, because our substrate can still bind, but our enzyme function is decreased, our enzyme role is decreased, and the rate at which these reactions occur significantly decreases because these substrates cannot go through that final step or that final haircut, that final transformation to become a product. And that is why our Vmax decreases. And we can see by an increasing inhibitor concentration right here, again, we're going to shift to the left, but our Vmax is going to decrease as well. So for non-competitive inhibition, one of the biggest concepts we need to know is our Vmax decreases when there's an increased amount of inhibitor present. So just as a refresher, non-competitive inhibition, our inhibitors are going to be heavy metals, or consider a Lewis base. They are going to attach to the allosteric site, which is this binding site right here, and they're going to change the tertiary structure of our enzyme. And as a result of this change of tertiary structure, our Vmax is going to decrease when we have a higher level of inhibitor present. But I forgot to tell you guys one thing. How do we reverse this? To reverse non-competitive inhibition, we use a chelate to react with the metal. Anytime you see non-competitive inhibition, I want you guys thinking of chelate right away. Chelate should be your spark words. Okay, let's talk about spark words. Chelate, to reverse non-competitive inhibition. Vmax, a decreasing Vmax should be another spark word. And then allosteric site should be another spark word. Honestly, everything on here is spark words. Memorize all of these starred concepts right here, because these are going to be great differentiators, because he will ask you about the different types of inhibitions. Cool. Allosteric inhibition. Yeah. All right. Oops. Got a hole. Okay, we're getting there. We're getting there. I'm talking quite a bit. I don't even know how long I've been going for, so I apologize. I hope you guys are on 2x speed, because that will make it a lot easier for you guys. All right, let's get into it. And I apologize again. This video is going to be coming out late, but it's going to be hopefully helpful. So allosteric inhibition. Allosteric inhibition is basically multiple steps. Basically, name of the game for allosteric inhibition is, let's say our final product is H down here. And one of the main reactions to occur or to kick this off is going to be E1, or enzyme number 1. Enzyme number 1 is going to, like, man, I want to use glucose. You know what, screw it. We're going to use glucose as an example. So, Biochem 2 topic, glucose is going to react with an enzyme right out of your blood, and it's going to transform and eventually turn into this thing called pyruvate. So let's go glucose. Eventually, there's a ton of other reactions that occur in here, but this is the easiest example I can think of. And enzyme 1 is going to initiate this beginning thing. So allosteric inhibition is our product coming back to inhibit this initial enzyme to shut it off so no more product is made. So if we are taking a ton of glucose out of our blood and we are creating a ton of pyruvate, and we just start getting a ton of accumulations of pyruvate down here, but we are not using it, and there's just a huge buildup of pyruvate, our body will sense that, and pyruvate will basically be an inhibitor of this beginning enzyme. Our overaccumulation of pyruvate will come back to this initial enzyme and say, hey, we have too much down here and we're not using it. You need to slow down. You need to, like, slow your roll, man. You are pumping out way too much pyruvate and we don't know what to do with it down here. So pyruvate is going to come back and inhibit this enzyme right here. So no more pyruvate is made until all of this is used up, or all of this is used for other functions and the pyruvate levels decrease. That is allosteric inhibition, our product coming in back and inhibiting an enzyme. So multiple steps. Final product inhibits a previous reaction. And again, only if the product is not being used up. Allosteric functions. Allosteric enzymes function as a catalyst and an inhibitor. So basically, if we need pyruvate and we have a super low amount of pyruvate, our enzyme will be that catalyst and say, hey, glucose, get out of the blood. We need to make some pyruvate. And it will start cycling those glucoses in through that enzyme and start cranking out a ton of pyruvate. But on the other end of things, it can be an inhibitor, in which if we have too much pyruvate and we're not using it, it will come back to the enzyme and say, hey, you need to slow your roll. And that enzyme will be like, glucose, hey, I don't love you anymore. We need to go our separate ways. We need to take some space, and I'm not going to react with you for a little bit. I'm going to inhibit you from turning into pyruvate. It has two binding sites, one for the substrate and one for the allosteric inhibitor. And lastly, I want you guys to pay attention to is we have a sigmoid curve. Sigmoid curve should be a spark word for allosteric enzymes. Allosteric binding sites, whatever. You see allosteric inhibition, you are thinking sigmoid shaped curve. And lastly, basically what we need to know is the increased amount of inhibitor that we have, our sigmoid curve is going to shift to the right. It is going to shift to the right, and our reaction velocity is going to slow down. But as soon as our inhibitor levels drop, our reaction or our curve is going to start shifting back over to the left because our reaction velocity can start speeding up a lot quicker, and we can get these reactions going off. Further to the right, slow the reaction, uses negative feedback loops, which is basically just product coming back and saying, hey, we have too much, shut off that enzyme. Yeah, I don't think I'm missing anything too much for that. Lastly, I do want to touch on this again. Look at the X and Y axes here. In our allosteric inhibition, we just have a V and our substrate concentration. So we have our velocity and our substrate concentration. But when we pop up to non-competitive inhibition, we can see that it's 1 over substrate. And over here, if you could see it, I don't know if I can. No, those are shined in right there. We can see for actually, this is a great comparison. Allosteric, we can see we just have substrate, velocity. Non-competitive, we can see we have 1 over substrate, and then 1 over velocity. And then same for competitive, 1 over substrate, 1 over velocity, and then for our normal Km and Kmax, it's just velocity over substrate. Memorize that. So now we have energy, kinetic energy, energy due to motion, potential energy, energy due to position, chemical energy, type of potential energy. I'm going to fly through this because we do have one major concept that we have to talk about, and this is all just spark words. So chemical energy, type of potential energy, and our chemical energy is stored in bonds. So this is where endothermic, exothermic values come into play with the energy stored within our bonds. First law of thermodynamics. Memorize this. And also memorize this. Energy cannot be created nor destroyed, only transferred, which we all have a good concept of that. But we need to understand that delta E or delta energy is equal to Q plus W or heat plus work. Big concept we need to know right here is our delta E can be all heat but no work, but cannot be all work and no heat. Anytime we work or anytime anything functions to operate, there's always heat involved, no matter what. But we can have all heat and no work, but we can't have all work and no heat. And then work is stored as ATP. Sweet. Second law of thermodynamics. Entropy is the measure of randomness, and that is going to be represented as delta S. Enthalpy is going to be delta H, bond making and breaking. We've already seen that concept over with endothermic and exothermic graphs. Again, right here, endothermic break bonds, energy into system, exothermic making bonds, energy out of systems. Work potential, delta G, big concept right here. Delta G, work potential. So anytime our work potential is greater than 0, that means we need to put energy into the system to get this reactions to occur. So that's basically just activation energy. We need to input a little bit of energy to get these reactions to go. So our delta G is going to be greater than 0 because we need to input energy to get this reaction to occur. Now, if our work potential is less than 0 or delta G is less than 0, that means we don't require any additional energy to throw in. We don't need to throw in any energy to these systems. And for the most part, they function spontaneously because we don't need any extra input of energy. They already have the required energy to just get crack-a-lackin' and get these systems or get these reactions to go. And it's basically system into surroundings. So basically, this is an exothermic reaction right here because we know that we're going to have a negative energy value here. Anytime you see a negative, you should think that your delta G is less than 0. And that is just signifying that we have the required energy to make these reactions to occur. And anytime our delta G is greater than 0, we are thinking positive because we have to input energy to get these reactions to go. Yeah, I should talk about this. This is basically just comparing delta G's. So we know that glucose, okay, this is biochem too, all over again. Sweet. So glucose plus a phosphate will create glucose 6P plus H2O, but we know we need to make bonds here, or we need to get this stuff to go. But to make this happen, our delta G is 14 just for this reaction alone. We know it's a positive value, which means we need to input energy to get this thing to go. So we will couple this reaction with ATP here because ATP provides energy. We provide negative 31 kilojoules per ATP. So by pairing it with ATP, we have that input of energy we need to get this top reaction. Oh, we know when we add ATP, we can use the energy from ATP to put into this delta G to get this reaction to go, or to get glucose plus a phosphate group to turn into glucose 6P. And basically right here, what you do is, if you want to simplify the equations and add these together, you look for you look for similar structures on opposite sides. So like right here, we can see we have an H2O down here on ATP, and we have an H2O on the opposite side right here on this glucose transformation. So as a result, we can simplify our equation down to glucose plus ATP equals ADP plus glucose 6P, because we can just remove like terms. We can remove H2O, and what we'll do is we'll just add these energy values together. And so delta G is now negative. Delta G is negative 17 kilojoules, which means this reaction can occur without an extra input of energy after everything's been coupled together. ATP, 5-carbon sugar, nitrogenous base, 3 phosphates, work potential, negative 31 kilojoules. ATP will always have negative 31 kilojoules. Mitochondria. Okay, this is the home run stretch right here. This is the last subject we need to talk about. Mitochondria, organelles. It's an organelle within our cells. It has a dual membrane, and it's the site of ATP synthesis. And we're going to be talking about inner and outer mitochondrial membranes, basically. So we have our matrix in the center. We have our inner mitochondrial membrane right here, and then we have our outer mitochondrial membrane right here. And this little space in between is referred to as the intermembrane space. And this next topic we're going to go into talks about this heavy, but some more memorization we need to know. Within the membrane of the mitochondria, within the inner membrane of the mitochondria, so inner membrane right here, woo! We're going to have a couple things we need to memorize. First thing we need to memorize is pyridine-linked dehydrogenase. Anytime you see pyridine-linked dehydrogenase, I want you immediately thinking of NAD plus and NADH. Stars, these are star topics right here. Pyridine-linked dehydrogenase, think NAD plus and NADH. And lastly, our B vitamin that we need to know is niacin. We need to know niacin goes with NAD and NADH, and it's pretty easy to memorize because they're all N's, and it goes to pyridine-linked dehydrogenase. Number 2, flavin-linked dehydrogenase. Flavin, we need to know FAD and FADH. We need to know those go with flavin-linked dehydrogenase, and I just like to call it Fs. We see FFF, we know those all go together. And then our B vitamin we need to know is riboflavin. Anytime you see riboflavin, you should be thinking riboflavin-linked or flavin-linked dehydrogenase, FAD, and FADH. Cytochromes, heme iron. What I want you guys to know is cytochromes are heme iron. They are heme iron groups, and they are bound to nitrogen. That's basically all we need to know. And it also involves iron, which I hope you guys know iron, Fe2 plus, Fe3 plus. But cytochromes involve heme iron. So anytime you see heme iron, you should be thinking of cytochrome. And it's also bound to nitrogen. So lock that into your brains. Non-heme iron protein. It basically says in the name, it's an iron protein that's not bound to a heme group, but it is bound to sulfur. So anytime you see this example right here, S, we know that this iron is bound to a sulfur, so it is going to be a non-heme iron protein, because if it was a cytochrome or heme iron protein, it would be bound to a nitrogen. And then ubiquinone, Q10, basically all I want you guys to know is it's not a polypeptide. That's realistically all I want you guys to know about that. Oh, last topic. Also, memorize 220. 220 kilojoules. We're going to be talking about with the electron transport system, and it is just going to be a major topic that we are required to know. Yeah. Okay. Here we go. I even drew a nice little pretty picture for you guys that we're going to get to in a second. So, electron transport chain, it occurs in the mitochondria. So, biggest thing I want you guys to understand about the mitochondria, it is one of the few organelles in our body that can generate energy from oxygen. Anytime you think oxygen, you should be thinking about the mitochondria. And oxygen will reduce to form water with electrons donated from NADH and FADH2. We'll get into that in a second, but another good thing to know is NADs or NADHs generate 2.5 ATP and FADHs generate 1.5 ATP. Now, in the electron transport system, electrons will flow through a chain of membrane-bound carriers, and as electrons travel from a higher energy state to a lower energy state, they will release energy. The energy released from this movement of electrons will allow hydrogen ions or protons to cross from the matrix into the intermembranous space of the mitochondria. I'm trying to figure out just spark notes to give you guys right now before we jump into the picture. Basically, what I want you guys to know is name of the game for the electron transport system is a collapsing proton gradient. When you think ETS system, think collapsing proton gradient. And the reason I say that is maybe if you guys have been doing some practice questions, this term might appear in a question. I'm just saying. So, electron transport system generates and helps create ATP based off of a collapsing proton gradient. And it has all these different systems that are involved. We can see like this complex system right here. And come back after I go through my diagram, come back and memorize the system, because I did go and do some extra research. Because last try I did explain this pretty well, but I was missing some key concepts that I went and got educated on to provide a well-rounded experience for you guys. And then afterwards, also come back and read through some of these complexes as well, because it will make a lot more sense once I walk through it. All right, let's get to the diagram. Here we go. Holy cow, you guys are probably thinking, holy crap, Ryan, what is this? Well, I'll tell you. Yeah, okay, let's get into it. So, basically, name of the game is to create a proton gradient out here in the intermembranous space. So eventually we can come down here and blast protons back into the mitochondria to help generate the reaction or the creation of ATP. But how do we get these protons out into this intermembranous space? So this is basically going to go in a clockwise order here. And complex 1 and complex 2, which are represented by comp 1 or comp 2 and comp 1 right here, they both accomplish the same thing, but just different mechanisms to do so. So we'll talk about complex 1 right here. So complex 1, how are we going to get these protons and electrons to allow these channels to open? So what we're going to start off with is NADH, and I want you guys to associate NADH and NAD with complex 1. Basically, what's going to happen is NADH here is going to also locations. Sorry, I don't mean to bounce around like this, but we need to know. Yeah. Hang on. Cytosol. Remember in this space, I did a little error, a little oopsie right here. So all of these complexes, CoQs, like site C, complex 4, all of these are embedded within the inner membrane of the mitochondria. So on the inner surface of the inner membrane, we have the matrix down here, where a lot of these reactions are occurring. Within our inner membrane, this is where we have a lot of our protein complexes, our complex 1, 2, CoQ, complex 3, and then up in here, this is our intermembranous space in between the inner membrane and in between the external membrane. And this is referred to as just basically the cytosol, or what you guys will see it as. So to kick off this reaction, to eventually get protons all the way back in through there, what's going to happen is NADH is going to come up and interact with complex 1. And what NADH is going to do is it is going to reduce complex 1 by giving it an electron. We are giving something. Complex 1 is gaining something, gaining whatever you want to call it, gaining an electron, and it is becoming reduced. And after that electron is given off, our NADH is going to want to get rid of that hydrogen. So all we're going to do is we're going to give away an electron into complex 1, and we are going to separate NADH, or our hydrogen, from our NADH right here. So we can see we have NAD and an H. Sweet. So we'll move over to complex 2. Complex 2 requires a couple more steps. Basically, complex 2, how it's going to kick off is succinate is going to be transformed into fumarate by FAD coming down here and removing hydrogens from succinate. FAD is going to come down here and remove hydrogens from succinate, and as a result, fumarate is going to, or succinate is going to be oxidized because it is losing these hydrogens in this process over to fumarate. So if something, like if succinate is losing something, it is referred to as being oxidized. And FAD right here, it is gaining hydrogens, so it is going to become reduced. We are gaining something. And very similar to complex 1, FADH2 is going to come up here, interact with complex 2, drop off an electron, and it is going to dissociate this hydrogen again. And it's just going to turn back into FAD plus just 2 separate hydrogens floating next to it. Sweet. So how do we get these hydrogens out through these pores and into this intermembranous space? Well, what's going to happen is, with these electrons bind to these complexes are gaining a ton of energy that they're not a big fan of. So what they're going to do is they are going to shuttle these electrons over to CoQ. And CoQ is going to temporarily hold these electrons basically on layaway and say, hey, I'll hold on to these for a split second, but I don't want to hold them forever. And when complex 1 gets rid of this electron, and because basically what's happening is, and I mean, I watched a YouTube video on this as well just to get these finer details for you guys, so I will basically Ninja Nerd electron transport system, go watch him if you want a more in-depth and probably better explanation than this. But basically complex 1 is gaining a little bit of energy with this electron, but when this electron is removed and this complex loses energy, this pore right here opens and it allows this hydrogen to flow out into the cytosol or into the intermembranous space. Cool. So to recap, both of these complexes gain electrons from these little reactions right here, and once they get these electrons, we are going to transfer them over to CoQ and reduce CoQ with these electrons, because CoQ is gaining something. And when this electron leaves complex 1 right here, this pore opens and this hydrogen is able to flow out into the cytosol or the intermembranous space. And complex 2 is kind of just a carrier for an electron, passes on to CoQ. So now CoQ is eventually going to say, hey, I don't want these electrons. I want to get back to my normal resting state. So CoQ is going to pass these electrons on over to complex 3. Complex 3 is going to be reduced from CoQ, and CoQ is going to be oxidized from complex 3 because CoQ is losing something and complex 3 is gaining something. So now these electrons are over here on complex 3. And complex 3 is like, hey, I don't want these. And so complex 3, again, is going to pass them down to site C. Site C is going to hang on to these electrons for a second, but wait. We see a little channel protein here with complex 3. Well, when complex 3 gets rid of these electrons, again, this channel is going to open, and now this free-floating hydrogen that we had down here is going to come over here and go, oh, I want to leave. And it's going to fly out through this channel pore. So now we're starting to get an accumulation of hydrogen protons out in this intermembranous space from both complex 1 and complex 3. These minor details you really don't need to know. The big concept I want you guys to know here is that hydrogens are getting out into the cytosol or the intermembranous space. And if we have a ton of hydrogens in our intermembranous space, hydrogens are an acidic component. So the more hydrogens we get in this intermembranous space, our pH is going to drop because we are adding acidic components into the cytosol. And if we are having hydrogens leave from the matrix, what do you think is happening? We're getting rid of acidic components. So our pH is going to increase with the amount. Our pH is going to increase when we get rid of more and more hydrogens out into this intermembranous space. So now we're here. We went from complex 3, we opened up this next channel protein, we'll release these hydrogens out into the intermembranous space. And then we also transfer these electrons over onto site C. Now site C is going to do the exact same thing. We're like, hey, we don't want these electrons, and we're going to come plop them down onto complex 4. Now, complex 4 is going to have a little bit of a different reaction. Complex 4 is going to get these electrons and say, hey, I don't want these, but I have nowhere to put them. Well, what are we going to do? We're going to send them back into our matrix. We're going to take them from the inner membrane of complex 4 and put them back into the matrix. And when this occurs, we have free-floating oxygen and free-floating hydrogens inside our matrix, but we just don't have the electrons or the energy to combine these to make H2O. But as soon as complex 4 is able to get these electrons, complex 4 is able to initiate the creation of H2O through bringing these electrons down here into this concept or into this little conjunction or reaction. And as a result, we are able to make H2O in this step. If you guys are to correlate anything, correlate complex 4 with H2O creation. Sweet. One final step to the puzzle. What are we going to do with all these hydrogens up here? Well, we have been pumping hydrogens out this entire time, so we are creating a huge gradient between protons, between the matrix and the intermembranous space. So we have a high concentration of hydrogens out here in this intermembranous space now, and we have a lower concentration of hydrogens in this matrix. So what we are able to do is we are able to take all these hydrogens and bring them down here to a channel protein. And all we're going to do is, since there's such a high concentration gradient, these hydrogens are going to start flinging back into the matrix and providing an extra little bit of energy to initiate the creation of ATP by allowing ADP and PI to bind together and create ATP. So we basically, the name of the game for this entire thing again is transfer of electrons, creating a proton gradient from all these little reactions right here. We are creating a proton gradient over this entire system here. And we are going to be pumping hydrogens back in at this very end step to eventually create ATP. That is the main role of the electron transport system, is to create ATP. And we just do that by, again, creating a proton gradient and collapsing it to give this burst of energy right here. And we're also creating just a little bit of H2O. So memorize complex 1, complex 2, CoQ, complex 3, site C, complex 4, and this proton gradient. All we need to know is I'm just going to create just a big arrow just to overly simplify this. Complex 1 goes to CoQ, complex 2 goes to CoQ, CoQ goes to complex 3 goes to site C goes to complex 4 creates H2O. And this entire time we are creating a proton gradient. These protons are going to come flying back in so we can eventually create ATP. Woo! That was a lot. I hope you guys are kind of picking up what I'm putting down. It is a lot. I understand that, but you guys are smart and I know you guys can do it. So we'll cover just some last things down here. Again, go through and read some of this after. I hope I walked through and gave you a good walkthrough of everything that happens, because a lot of these are overly simplified forms. So it should be a little bit easier for you guys to walk through. Now we'll just talk about inhibition of the ETS. And actually what I'm going to do is I'm going to do split view. So with this system set up over here, crap, I can't get rid of these arrows. Arrow, bop, bop, bop. Oh, bop, bop, bop. All right. So now we're going to be talking about inhibitions. So basically, inhibitions is just basically shutting down the electron transport system at different spots. So we'll start at spot number one. No ADP is present. And before I get into it too, I want you guys to look at the axes yet again. Over here is oxygen consumption. We can see the pressure of O2, and we can see these slopes are going down, which means our pressure of oxygen is decreasing, which means we are using oxygen for these reactions. We are using up the oxygen present, and at these plateaus, we can see that we have no oxygen consumption present. Sweet. With that concept out of the way, let's get into it. So, spot number one, no ADP present. And we can see that we are consuming oxygen until we get to this plateau, which is represented by not having ADP. And that means we are shutting down this electron transport system because we have no ADP to react. And where that is occurring on this chart over here on the right is right here. If we do not have any of this ADP, we cannot generate ATP. So why go through all of these reactions to create a proton gradient if we can't even react it down here? So how do we bypass that? How do we get over this inhibition of not having ADP and start consuming oxygen again? Well, we just add ADP. As soon as we add ADP back into the system, this whole complex starts over again. It gets ripping again because we have ADP and we have reactants to react the hydrogens with. Now, number two, adding rotenone. All we need to know is it impacts complex 1, so it shuts down complex 1 over on this side. So if complex 1 is shut down and we're not consuming any oxygen, how do we get this system functioning again so we can start using up this oxygen? Well, all we do is add succinate, because if we look, complex 1 and complex 2 both go to the same area. So if we shut down this complex over here, we just have to activate complex 2 to still get electrons over to CoQ. So all we have to do is add succinate, and succinate will go through all these reactions again to get these electrons over here and get CoQ with the electrons that it needs. So to bypass this inhibition right here with rotenone, all we need to do is add succinate to kick in complex 2 right here. All right. And again, allows CoQ to be reduced because we're adding electrons to it, reducing CoQ. And now we'll talk about oligomycin. And oligomycin impacts complex 5. And honestly, I should have drawn complex 5. So this channel protein right here is complex 5. This little last channel protein is complex 5. So as soon as we add oligomycin to it, we are shutting down this channel protein right here. And which means we can't get our proton gradient to collapse to create ATP or to use up some of this oxygen. So how are we going to what it also does is inhibits ADP from getting back into this matrix. That is actually a bigger keynote. It does not allow ADP to cross the mitochondrial membrane to get back into here to resupply our ADP supplies. So how do we get by that? We add DNP. DNP, what is DNP? Dinitrophenol. It is an uncoupler. It allows for oxidation reduction reactions without making ATP. So basically allows us to do all these NADH reactions without even using ATP. And basically what this is beneficial for is hibernation and infants trying to stay warm. And the biggest thing I want you guys to note with this is brown fat. Brown fat is a main mechanism for this. And basically what an uncoupler does is it allows for our just reactions to go, but we really don't need to produce as much ATP. We don't have to use as much of the molecules within our body to supply ATP, because if we're doing all these normal reactions and generating ATP, we need to continuously eat food to continuously provide fuel to make these reactions to happen. But as soon as we add DNP, we really don't need as much food to fuel our body since we're not generating as much ATP with a lot of our reactions. So the star points right here is it decreases the proton gradient, it decreases the work potential, decreases ATP production, it increases our oxygen consumption because we're still able to go through all these reactions, but we're just not really using up as much ATP as we were, but it decreases our efficiency. And why does it decrease our efficiency? Well, we are still doing all these continuous reactions, but we're not producing ATP for our body. So the efficiency at which we are doing this stuff just decreases to such a significant rate because we're just not providing the normal amount of ATP we are producing. So the efficiency of these reactions decreases because we are not producing the normal amount of ATP that we do. All right, last couple that we're talking about here. Honestly, all I want you to know for CN right here is it impacts complex 4, which is this complex right here over here on this side. And my Apple Pencil doesn't want to work with it. It impacts complex 4 right there, and it's just irreversible. Shuts down complex 4, and yeah, it basically just shuts down this entire process because we can't get rid of these electrons and can't create CO2. So it basically just shuts down our entire electron transport chain. And last one we want to talk about is antimycin. It impacts complex 3 and is just compensated by adding ascorbate. This might have been a little rushed, and I do apologize. I should have been on top of this a little bit quicker, but Tri4 has gotten quite busy. So I'm going to upload this as soon as I can and get it out to you guys. And I wish you guys the best of luck on your exam, and I hope I could provide some clarification on some of these topics. You guys have been great this trimester. Keep it real. Keep it 100. Be the best you guys can be. Adios.